Because there is an increasing number of electronic devices on the public power grid and network communications via data lines, there need to be measures taken to prevent mutual interference caused by electromagnetic interference, commonly known as EMI. And these measures are becoming increasingly important. Protecting the wired interfaces against transient overvoltages is particularly important. Now, filter circuits, they are placed at the interfaces of the devices, and they not only attenuate high-frequency emissions and, therefore maintain radio protection, but they also reduce transient overvoltage directly at the input of a device, so the functions of the devices are not impaired. Now, today's episode, we are talking about transient suppression at different interfaces. Welcome to today's Wurth Electronics What's Up podcast. You're listening to Wurth Electronics What's Up, a radio podcast where each week we're seeing what's up in the world of electronics and PCB design. We're going to be checking in with leading industry experts, and our very own Wurth Electronic technical specialists are going to shine a light on some of our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Make sure you tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. So as we mentioned, today's episode is all about transient suppression at different interfaces. Basically, the following interface variants can really be distinguished, and each of which requires similar filter topologies. We have grid interfaces, for example, the 230-volt mains connection. We have asymmetrical signal interfaces and also symmetrical signal interfaces. Now, in this context, grid interfaces mean the interfaces between the power grid and consumers' equipment. Here, line filters are being used to attenuate interference emissions from devices into the power grid and protect a device from interference from the grid. Signal interface filters, they are designed for lower operating currents and voltages. Now, the requirements for the filters differs in the type of signal transmission, and it can be symmetrical or balanced over two data lines, or it could be asymmetrical, which is unbalanced via one data line and the ground. Although symmetrical interfaces are characterized by low interference emissions and higher interference immunity, the signal quality is affected by transient interference signals, differential mode interference, and also common mode interference. In today's episode, we are going to describe the structure of various interface filters that can help ensure signal integrity and also protect against these transients. Circuit diagrams of the filter circuits, also information on component selection, and some everyday examples will help us understand the easy transfer to another network or signal interfaces. Now, before we get further on, we do want to remind you that we understand not all podcast streaming platforms allow for pictures and videos, or you might be on the road, so pay attention to the road here. But if you are interested in downloading the photos, the videos, and any links associated with today's episode, please visit our website at www.we-online.com/podcast. So first, we're going to discuss the EMI filter of an asymmetrical signal interface with transient protection. While unbalanced signal interfaces only use one data line per signal, interference emissions and interference immunity requirements are generally higher than with balanced signal interfaces. In our first image, we are seeing a possible filter circuit for attenuating interference emissions and ensuring interference immunity. A digital square wave signal with an amplitude of 5 volts and a frequency of 5 megahertz on the data line is what we're going to look at first. Now, the standard value of 90 ohms is assumed for the impedance of long data signal lines, and there's a voltage of 5 volts DC at 2 amps on the supply voltage line. Now, since the requirements for the filter circuits for the data line and the supply voltage line are different, then the filtering of the data line is what we're going to be talking about first. In our image shown here, we see a filter on the data line of an unbalanced signal interface. Now, to attenuate high-frequency interference on the data line, the two impedances shown here, Z sub 1 and Z sub 2B, form a low-pass pi filter with the inductor. Protection against the transient overvoltage is ensured by a transient protection device, which is Z sub 2A. So let's talk component selection. First, L sub 1, that is dimensioned and selected where the surface mount ferrite or an RF ferrite can be used here. Further information on the use of inductors or even surface mount ferrites can be found in a couple more attached application notes that we have, ANP 025, also ANP 129. The ohmic or resistive components of the impedance of the surface mount ferrite should be as low as possible, up to the fifth harmonic of the signal frequency. And the impedance at this frequency should be less than 1/10 of the system impedance to avoid affecting the useful signal. So in our example, the fifth harmonic is at 25 megahertz, as the signal frequency is a 5 megahertz square wave. Since the system impedance in this example is 90 ohms, the impedance at 25 megahertz should be at most about 1/10, so no more than 9 ohms. In our next image, it shows a typical impedance curve as seen in the data sheets. The proper inductors in the example of a surface mount ferrite can be selected with the help of our component selector Red Expert. In this image here, we see impedance characteristics, the WE-CBF surface mount ferrite 74279273. So next, let's figure out that Z1. Now, Z sub 1 or Z1 is a capacitor, and it can be optionally used to attenuate interference frequencies in the RF range above 500 megahertz originating from the driver. Now, based on practical experience that we have, then an attenuation that you want is of 10 decibels. It should be achieved at 500 megahertz, resulting in a voltage ratio of a V out divided by V in of approximately 0.316. The capacitor impedance Z1, which is capacitive reactance, can be determined using the voltage divider seen here. So V out is the voltage across the capacitor, which is that Z sub 1, and it is measured in volts. V in is the total input voltage to the circuit, and V out divided by V in is the voltage ratio from the attenuation. Ri is the internal resistance of the signal source or system impedance measured in ohms, and that Z1 is the capacitor impedance or capacitive reactance, also measured in ohms. So given that Ri is 90 ohms, then the calculated Z1 from our first original calculation is approximately 42 ohms. So next we need the capacitance value, and this is required for attenuation at a frequency of 500 megahertz. It can be calculated as follows. That is, the capacitance equals 1 over 2 times pi times frequency times Z1. So we're going to substitute our known values. We have the capacitance equals 1 over 2 times pi times 500 megahertz times 42 ohms. It's going to give us roughly 7.5 picofarad. So based on these calculations, we recommend the WCAP CSGP, and this is an MLCC capacitor with a value of 10 picofarad and a voltage withstand rating of 25 volts. This capacitor is an NPO ceramic type, so it offers more stable voltage and temperature behavior compared to the X7R ceramics. When considering these critical factors, such as signal integrity due to the cutoff frequency of the filter and the capacitive load, it's really important to account for parasitic capacitances of the conductor tracks and, if necessary, interface connectors. Now that we have Z sub 1, we need Z sub 2, and this consists of components for transient protection, which is Z sub 2A, and a capacitor, Z sub 2B, where the parasitic capacitance of the transient protection device, such as a TVS diode or a surface mount varistor, additionally contributes to the capacitance of the pi filter. If the capacitance of the transient protection is high enough to achieve the required attenuation of 3 decibels at 25 megahertz, again, our V out divided by V in equals 0.707, then the capacitor may not even be needed. Now, the advantages of a varistor compared to a TVS diode are the high parasitic capacitance, a short response time, and the ability to absorb much more energy with the same component size. So the calculations can really be quite simple once we have our needed numbers. The V out divided by V in is the voltage ratio from the attenuation. ZL1 is that impedance of the ferrite at 25 megahertz, and it's roughly 10 ohms. And then Z2 represents the total impedance of Z2A and Z2B measured in ohms. So from this, we calculate the impedance and the capacitance that's required. So we know that our impedance is roughly 25 ohms, and therefore the capacitance is needed to be around 250 picofarad. The operating voltage of the varistor must be greater than the maximum operating voltage of the system, which here is 5 volts. So considering a safety buffer of 15%, then the maximum operating voltage of the varistor is VDC greater than 5.75 volts. Based on this value and the available space in the application, then a surface mount multi-layer varistor is selected, which serves as the basis for the decision. So in this case, we're using the WE-VS, and this varistor, whose operating voltage is 5.5 volts and is therefore slightly below the required operating voltage, can be used. So once the varistor has been selected, the following calculations determine whether the correct selection has actually been made. Now, according to IEC and EN 61000-4-5 standard, the test pulse for surge between line and ground is V surge equals 0.5 kilovolts, and the source impedance is 42 ohms. To make our calculations a little bit easier, we specify the clamping voltage during the current surge as twice the breakdown voltage. So this value is slightly lower than the actual clamping voltage of the varistor at the surge current. It's 2 times 8 equals 16 volts versus the clamping at 21 volts. So the varistor voltage, which in our calculations is going to be labeled as V sub VAR or V sub BR, this can be found in the varistor datasheet. And the peak varistor current can be calculated using the numbers that we actually know. I sub clamp is the peak current of the varistor measured in amps. V surge is the test pulse voltage for surge measured in volts. VBR is the varistor voltage or breakdown voltage at 1 milliamp measured in volts. And the Z source is the source impedance as per IEC EN 61000-4-5 standards measured in ohms. So we're going to go ahead and substitute those known values. Now, considering the varistor volt tolerance of 25%, the max clamping current is 11.62 amps, and therefore it's below the max peak current of the varistor, which is 30 amps. Next, we want to calculate the energy consumption and the power loss. To simplify our calculation, we assume that the pulse is a square signal with a pulse duration of 20 microseconds, and the maximum clamping current is 11.6 amps. The approximate energy can be calculated with twice the breakdown voltage and the I clamp max. So our formula is the energy consumption of the varistor in joules equals 2 times the varistor voltage or breakdown voltage at 1 milliamp times the maximum clamping current times 20 microseconds. So substituting those values that we know, we get 3.7 millijoules. For this example, we are going to use the surface mount varistor WE-VS with a capacitance of 200 picofarad. To achieve the necessary capacitance, an additional capacitor with 47 picofarad in size 0805 can also be used in this case. The selected capacitor we went with is WCAP CSGP. Next, the filter for the supply voltage cable entering the device is created. And in this image, we see a power supply line filter of an unbalanced signal interface. Generally, transients are filtered at interfaces against the housing, and that's shown with the housing symbol. To enable a connection between the negative ground to the functional ground, the GND of the circuit board, and still attenuate the interference coming from the cable, a surface mount ferrite is used between the housing ground and the GND. The capacitor and the parasitic capacitance of our Z sub 5A drain RF emissions with respect to transient voltages coming from the cable to the housing ground. A decoupling capacitor with 100 nanofarad is used as a standard to determine our Z3. An X7R ceramic capacitor with sufficient high-rated voltage should be used here so as to not run into the voltage bias effect and to lose capacitance. Our Z4A is a surface mount varistor with a channel input capacitance of 200 picofarad. To achieve the necessary capacitance for the filter, an additional capacitor of 100 nanofarad is usually used as a standard for our Z4, which should be the same capacitor as Z3 and Z5B. Varistors, which is Z5A and Z4A, should be the same component. L2 and L6, those are surface mount ferrites, where the rated current should be considered first, and this must be greater than 2 times the output current. In our example, it corresponds to 2 times 2 amps, it's 4 amps, and this is the minimum rated current of the surface mount ferrite. Supply voltage lines have no cutoff frequency and a very low source impedance of roughly 2 to 9 ohms, and that's our Z out. As the noise source is the voltage line, all other signal sources on the electronic board will create RF noise to the voltage network, which must then be considered. So this means that the impedance, our ZL2 or ZL6, should be as high as possible across the entire signal frequency range, typically 30 megahertz to 1 gigahertz, to achieve sufficiently strong attenuation. The selection of the proper surface mount ferrite should actually be done using Red Expert component selector, and this is to get the right impedance over the relevant frequency range. The ferrite selected here is our WE-CBF surface mount EMI suppression ferrite bead. It's 742795252. The impedance chart that we see next and the electrical properties from the datasheet are also shown here. Here's a remark to the electrical grounding. Unlike earthing for electrical safety in the sense of the low voltage directive, the ground is a reference point for high frequency signals in terms of EMC. Accordingly, the reference ground must have a low impedance and it must be free of high frequency offset signals. It also needs to provide a reference point for filters and TVS components. The best reference is a very conductive metal housing. Next, we're moving on to EMI filter of a symmetrical signal interface with transient protection. So balanced signal interfaces use differential signal pairs to transmit information and to attenuate common mode interference. However, these interfaces are still susceptible to radiated electromagnetic interference, or EMI, and the coupling of transient voltages and currents. So to reduce unwanted interference that can affect signal quality and system operation, additional filtering of the interface is essential, and a good EMI filter reduces electromagnetic emissions from the signal source to the cable and vice versa. But it also limits transient external interference to a more tolerable level, and it has only a negligible effect on the signal integrity of the interface. Our next image here shows a possible filter circuit for a balanced signal interface, and the circuit utilizes a soft low-pass filter to pass the signal in differential mode while attenuating common mode components. A symmetric low-pass filter allows differential mode signals, which carry the essential information, to pass through unimpeded. Conversely, common mode signals, which are noise components of the signal, are attenuated or dampened by the signal. TVS diode array provides transient voltage protection, and these spikes are sudden, unwanted bursts of high voltage that can damage electronic components. When a transient overvoltage occurs, the TVS diodes limit the voltage and divert the transient impulse current from the circuit to the ground or the housing. Next, we're going to talk about USB 2.0 interface, and this is a widely used interface for data and power transfer between electronic devices. It provides a signal bandwidth of approximately 240 megahertz and an impedance of 90 ohms. A typical power supply for USB 2.0 is 5 volts with a max current of 1 amp. In regards to component selection for USB 2.0 interface, we have a few steps we need to go through first. First, determination of the L1. This is an inductor with high impedance for common mode noise. It allows for differential signals to pass with minimal attenuation in the relevant signal frequency range. L1 selection is crucial in terms of differential as well as common mode impedance needs. To ensure proper signal transmission, choke L1 should be selected according to the interface type and, of course, the datasheet information, taking these parameters into account. First, our system or interface impedance. This is labeled as Z system, and this can influence EMI filter design. You can find the system or interface impedance from the datasheet or the specs. Next, differential mode impedance, ZDM. And the choke impedance in the differential mode should be lower than 1/10 of the system impedance, which is our Z system, at the highest frequency within the signal bandwidth. This ensures minimal attenuation of the desired signals. Of course, our calculations then is just our system interface impedance equals our Z system divided by 10. Our common mode impedance, ZCM, should be as high as possible, especially at frequencies corresponding to expected interference. At center frequency, our common mode impedance should be higher than our Z system. Select a choke, that L1, with a high ZCM, especially at frequencies of expected interference. Make sure to pay close attention to the frequency response, current handling capability, and other relevant parameters of the choke. For this application example, a suitable choke with a differential mode impedance less than the max and a high common mode impedance is 744233900. This is our WE-CNSW high-frequency surface mount common mode line filter. After we have our inductor, we need to determine our Z1, Z2, Z5, and Z6. Our capacitors, Z1 and Z2, and our matching resistors, Z5 and Z6, all form a soft low-pass filter to limit signal harmonics or high-frequency noise produced by the controller. The values of the resistors depend on the signal controller and its imbalance or mismatch, and it must be selected according to the measurement results. The values of Z5 and Z6 are typically between 3 and 10 ohms. The capacitor values must be selected accordingly, and the values vary in range of 2.2 to 10 picofarad. Typical value for USB 2.0 is 4.7 picofarad, and that's especially with the WCAP CSGP, which is a ceramic capacitor. The resistors, our Z5 and Z6, especially 3.3 ohms, those are typically used for reflection damping and filtering in conjunction with the capacitors, our Z1 and Z2, and they're there to improve signal integrity and reduce interference. RF suitable types with a small body size should probably be used here. We also need to determine our Z3, Z4, our L2, Z7, and Z8. Our TVS diodes are Z3 and Z4, and components like L2, Z7, Z8, those all provide transient protection against voltage spikes and surges. To properly handle transient currents, consider the minimum rated current, the IR, of components such as L2 and the surface mount ferrite, our Z9. L2, Z7, and Z8, those are used for low cutoff frequency filtering, typically less than 1 megahertz. Our L2 should be a surface mount ferrite bead, and these are used for low cutoff frequency. Ensure the choke has an appropriate minimum rated current. To achieve broadband noise reduction, the surface mount ferrite, the WE-CBF, the surface mount EMI suppression bead, we used 742792032. You can see that in our attached table. These are the electrical properties of our surface mount that we just mentioned. Our Z7 and Z8, those are capacitors and varistors. The Z7 is a capacitor for low cutoff frequency filtering, and the Z8 is actually a surface mount varistor for transient protection. An example of a suitable capacitor for this is the WCAP CSGP. This is a generic ceramic capacitor, and for a varistor, the WE-VS surface mount varistor. Z3, Z4, these are TVS diode arrays, and they're transient voltage suppression arrays, such as the WE-TVS diode 824013-6 from the high-speed series, and they're used to protect signal lines against transient voltages. So it's important to note here that these components also exhibit parasitic capacitance, which must not be too high relative to the data transfer rate or the signal bandwidth. We also need to find out our Z9A and Z9B. So for high frequency, decoupling between housing and cable ground, that GND, surface mount ferrites, L10, and surface mount varistors, Z9A and Z9B, especially the WE-CBF surface mount EMI suppression bead and the WE-VS surface mount varistor, are used in combination with the capacitors. This filter selection helps reduce common mode interference and improves system stability. Ensure that the current carrying components are compatible with the required minimum rating current. We should also consider a power line filter with transient protection, and a power line filter of protection class 1 with a protective conductor. We can see this in our diagram attached. It contains all the components that are necessary for the filter circuit. Our choke, L1, decouples the load, for example, the power supply, from the mains with its common mode impedance. So this means that the choke is RF technically with Z1 and Z6, and Z2 and Z7, when the reference ground, the PCB ground to housing, carries interference potential. However, Z6 and Z7 are capacitors with low capacitance, around 200 to 470 picofarad, and they're inserted to dampen high-frequency harmonics of the switching power supply. The two capacitors should be placed on the circuit board of the power supply if the proportion of switching harmonics on the power supply side is high, or if the reference ground or the case ground does not form a high-frequency stable reference point. The chokes Z4 and Z5 are already partially covered by the leakage inductance of the common mode choke, L1, so Z4 and Z5 can also be provided for additional attenuation in the frequency range above 10 megahertz. A mains filter for an interface with a 50 Hz mains frequency and a voltage of 230 VAC serves as a calculation example. The maximum permissible leakage current on PE is 3.5 milliamps. For safety reasons, a maximum leakage current of 2.6 milliamps is assumed in our example, from which the maximum capacitance of the Y capacitor with the mains filter frequency equals 50 Hz, and the worst case voltage of 257 volts is calculated as the maximum capacitance of the Y capacitor, measured in farads, equals the maximum leakage current divided by 2 times pi times the mains frequency times the possible maximum value of the mains voltage. When we substitute our known values, we know that the maximum possible capacitance value of the Y capacitor is approximately 33 nanofarads. When designing the common mode choke L1, the current carrying capacity, the rated current IR, depends on the load, and the max ambient temperature and the maximum permissible leakage current must be considered. The inductance of the common mode choke is defined depending on the current waveform of the AC to DC converter. So for sinusoidal current consumption, a high inductance of greater than 10 millihenry is used, while for non-sinusoidal current consumption, such as a switching regulator, then the lower inductances in the range of 1 to 10 millihenry are used. In our examples, a sinusoidal current is drawn and a common mode choke with 10 millihenry is selected. And this current compensated mains choke we're using is the WE-CBF. In the next step, the Y capacitors Z1 and Z2 and the X capacitors Z8 are selected. Based on our experience, the required minimum attenuation at 150 kilohertz is 20 decibels in differential mode and 40 decibels in common mode. Common values for the filter corner frequencies are 15 kilohertz in differential mode and 10 kilohertz in common mode. The corner frequency represents the frequency at which the attenuation of a filter is 3 decibels. Given the required corner frequencies and required attenuation, we can easily calculate our capacitances. Now our FCDM, that is the corner frequency of the differential mode filter, and that's in hertz. FCCM is the corner frequency of the common mode filter, also in hertz. L1 is the inductance of the common mode choke, in Henry. L1 leak is leakage inductance, also in Henry, and that is derived from the L1 divided by 200, the empirical value. So based on these values, we know that a capacitance of 2.2 microfarad is used for CX, and a capacitance of 14.1 nanofarad is used for CY. In this graph here, we see differential mode, which is in green, and common mode in blue, and that's the attenuation by Z1, Z2, and Z8. The required attenuation of 20 decibels at 150 kilohertz is exceeded by 32 decibels in differential mode. The common mode attenuation of 40 decibels at 150 kilohertz can also be easily achieved with 43 decibels. For transient protection, a disc varistor is used in parallel to the X capacitor. Now, there are various approaches to the selection process, such as empirical testing of similar products, selection based on the specific electrical environmental conditions, or the surge test, and that's according to the standard IEC EN 61000-4-5. That's a fundamental EMC test. For our example, we will be using that fundamental EMC test. Now, when selecting the disc varistor, the maximum operating voltage is going to be found first. For safety reasons, this is calculated with a buffer of typically 15% above the supply voltage. With a mains voltage of 230 VAC, the maximum operating voltage is 264.5 VAC. In our table shown here, the size of the varistors depends on the peak current to be clamped. The higher the rated current, the larger the component. The disc varistor VVD with a maximum operating voltage of 300 volts is used as the basis for the decision. According to the standard that we just talked about, the voltage of the test pulse for surge between a conductor and a return conductor is 2 kilovolts, and the source impedance is 2 ohms for low voltage network connections between live conductor and neutral conductor. The breakdown voltage, seen as VVAR or VBR, can be found in the varistor datasheet. The peak current, which is I peak, can be calculated by taking the test pulse for surge, measured in volts, minus 2 times the varistor voltage or breakdown voltage at 1 milliamp, measured in volts, divided by the source impedance according to our IEC EN 61000-4-5 standard. And by substituting our known values, The clamped peak current is about 530 amps. To simplify our calculation, we specify that the clamping voltage during the current surge is twice the breakdown voltage. This value is slightly higher than the actual clamping voltage of the varistor at the surge current. You can refer to the diagram of the rated current versus the voltage in the data sheet. Our approximation gives us about 2 volts BR. Considering a tolerance of 10%, the max clamping current is 583 amps, and it's therefore below the max peak current of the varistor, which is 6,000 amps. Again, we want to calculate the energy consumption and the power loss. So to further simplify our calculation, it's assumed that the pulse is a rectangular signal that maintains its max current value over its 20 microsecond duration. Then the energy can be calculated with twice the breakdown voltage, that VBR, and the I clamp max, that's the maximum clamping current. So our energy consumption of the varistor measured in joules equals 2 times the varistor breakdown voltage at 1 milliamp times the maximum clamping current times our 20 microseconds. And when we substitute our known values, the energy to be absorbed by the varistor is 11 joules. The IEC EN 61000-4-5 standard requires at least one surge impulse per minute during testing. The varistor must be able to dissipate this energy. The power requirement can be calculated from the energy and the time between 2 surge pulses. And that's simply P equals W max divided by T. P is the power dissipated by the varistor in watts, and W max is the energy consumption of the varistor in joules divided by the time between the 2 surge pulses. So known these values, the power is calculated to be 183 milliwatts. The varistor would therefore also be suitable for a surge interval of 20 seconds, whereby the power would then correspond to 549 milliwatts and would be below the max power loss of the selected varistor, our 600 milliwatts. In conclusion, we have discussed the basis for transient suppression and some basic EMI filtering for both data and power interfaces. Thank you again for joining us for today's What's Up podcast. And we know that while some streaming platforms are making the switch to video format, there are still some that are audio only. So if you want to learn more, head on over to our website where you can download all the data sheets and additional technical materials. You can find all the images and tables discussed in today's episode. Found online at www.we-online.com/podcast. And if you're ready to get hands-on, you can easily order any of the components discussed today for surge protection, EMI suppression, and everything else by reaching out to your regional Wurth Electronic contact. You can also chat with our live team at Wurth Electronic Online or order directly through the MyWE customer portal. You're listening to Wurth Electronics What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Wurth Electronics specialists who are going to shine a light on topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast.